All right, everybody. Well, welcome to this edition of the Explorer session. I hope everybody has been having a fun time over the past few days. Hope everybody's been safe and taking care of themselves in these interesting times we find ourselves in. My name is Donaldo Canales, and I am one of the methodologists at Research Services, and I am also a PhD candidate in experimental psychology at the University of New Brunswick. So today's talk is basically just a quick course, a crash course to help you better understand your research variables and better guide you to choosing an analysis that is best suited to your data. I would also like to point out that today's presentation, I purposely designed it for beginners. I've purposely kept everything very, very simple, and I've really tried to aim this presentation towards people with little to no statistical background. So if you are a type of person with advanced knowledge in statistics and you run structured equation models all day long, you're more than welcome to hang out and review basic concepts with us. So just a quick roadmap of today's talk. I will begin talking about scales of measurement and why this is very important when trying to think about what statistical test is most appropriate for your data. And I'll also talk about a couple of design characteristics that should help you decide which statistical test to apply. And at the end, in the latter half of this presentation, I'm going to review 6 different types of stats that I think would be more than sufficient to meet most of your methodology or most of your analysis needs. So it first helps to begin by talking about scales of measurement, or sorry, variables, which will lead into scales of measurement. So in research, we have to make the distinction between different types of variables. Different variables have different types of qualities and have different properties. And one distinction when it comes to variables is the distinction between independent and dependent variables. The independent variables, which are also referred to as the IV, are thought to be the cause of some effect. So you have this variable that is either manipulated by a researcher or can be already existing in nature, and it's thought to be the cause of some outcome. It is typically used in experimental research to describe a variable that an experimenter has manipulated. In turn, the dependent variable, also known as DV, is thought to be affected by changes in the independent variable. So the idea here is that the independent variable produces a change in the dependent variable. Now, this distinction of independent and dependent variables is most closely tied to experimental methods. But in the real world, you cannot manipulate variables. So if a researcher has a lot of control over their participants and can manipulate various designs of their experiment, that would be considered an experimental design, but in the real world settings, we don't always have that level of control. So for example, if you were trying to test the effects of smoking on lung cancer, you can't ethically lock people in a room for 30 years and force them to smoke cigarettes. So we have to look at, we have to and come up with more unique and creative ways of testing these relationships. So this is where observational research comes in. In observational research, nothing is manipulated. You're just more focused on examining relationships and associations between different variables. So within a observational research context or framework, we refer to these variables as more as predictor and outcome variables. So predictor variable is analogous to the independent variable, which is the variable in your data that is thought to predict an outcome. And on the other hand, the outcome variable is thought to change as a function of the predictor variable. So in the real world, when researchers are talking, all these terms are used very interchangeably. I'm also very much guilty of that. So independent and predictor just kind of get used interchangeably, and dependent and outcome variable get used interchangeably. So it's also very important to understand that variables have different properties. They have different forms and very different levels of sophistication. And there's several different ways to think about these scales of measurements or these levels of sophistication, but one main distinction is the difference between categorical and continuous variables. So categorical variables are variables that are made up of categories, as the name implies. In its most simple form are the binary types of variables. This is just a variable with that represents two distinct types of things. For example, male and female, or disease present and disease absent, whether your patients are alive or dead, or any variable that takes a yes-no form. So disease present, yes, no, attended appointments, yes, no, those sorts of variables. The coding of these binary variables does not give any numerical information. It is simply just to distinguish between the variable that has the quality that you're interested in, and the other person who is absent of that same quality. Moving one step up are nominal variables. Now, this is an extension of the binary variable where there are more than two categories. So, for example, hair color would be one example. So we have people who are blonde, have brown hair, black hair, and red hair. So another example that's used commonly in research is marital status. So whether the individual is single, dating, common law, married, or divorced. So again, this is an extension of the binary variable. And it's also important to understand that the coding of these variables do not give any numerical information. You can't do math on any of these variables. You can report percentages. So you can say X amount of my sample had black hair and X amount had red hair, but you can't multiply these different values. You can't subtract them. You can't say, two blondes equals one redhead or something like that. You can't do any of those sorts of things. So it is a limitation of these variables. So they're simply just to categorize and group, but they don't give any numerical information. Next up is the ordinal types of variables. Now, these are nominal variables, but the categories are ranked according to some logical order. So typically these variables are ranked from low to high, or in some cases high to low, but I always advise people to rank them from low to high. One example of this would be medication compliance. So you can have somebody who has no medication compliance, partial medication compliance, and good medication compliance. So as you can see, the way these values are, the way these categories are ordered, there is an increase in magnitude. It's a new property that's introduced with the ordinal variables. Problem with ordinal variables is that the difference between the intervals are not meaningful. So think about a marathon. You have 3 people running a marathon. The first person, so you can order them in first, second, and third place, but the first person and the time between the first and the second place could be maybe seconds, and the time between second and third place could be, in the marathon, could be 10 minutes or 15 minutes. So we have information about the order which in the racers finished the race, but we don't have any information about the intervals in between the racers, the spaces in between the racers, and that's a very important distinction. So the next group of variables are continuous variables, and these are where the thing that you are measuring gets a distinct score on a scale. So one of the most common ones, and it's actually used a lot in the medical literature and other types of other disciplines, such as psychology, where I'm from. So these are the interval variables, where the difference is it's ordinal in the sense that there's an increase in magnitude. It is assumed that the differences between the magnitudes are roughly equal. So for example, if I gave somebody a scale from 1 to 5, the assumption that I'm making when I'm using this scale is that the difference between 1 and 2 is the same as the difference between 4 and 5. Likewise, the difference from 2 and 4 is the same as the distance from 3 to 5. So this is assumed that all the spaces between the intervals in the scale are the same. A score of 0 on interval scales usually doesn't mean anything. It's just a point on the continuum. So I could easily give you a scale to rate your level of confidence in some task from 1 to 5, but I can give you another scale that asks you to rate your level of confidence from -2 to +2. That would also be a 5-point scale, whereas 0 is in the midpoint. The 0 doesn't really mean anything. It's just an arbitrary point along the scale. One clear example of this is thermometers. So we assume that the difference between 10 degrees and 20 degrees is the same as the difference between 40 degrees and 50 degrees. But when you go to 0, it doesn't mean that there's an absence of temperature. It's a point along that continuum. And the next step up are the ratio variables. Now, this is when there is order, as in the ordinal variables. There are intervals with the interval variables. Also is a true 0. So that's very, very important. For ratio variables, a true 0 means that if you score a 0 on a ratio scale, there's literally absence of whatever that quality is. So there's an absence of the variable that is being measured. For example, medication dose. You can have any milligrams, you can have 0 milligrams. 0 milligrams means there is no medication. Number of pills dispensed in a day. 0 pills means nothing was given. Reaction times. I used to be involved in reaction time research. 0 reaction time means that nothing occurred. Money in the bank. If you ask me how much money I have in my bank, I have no money in my bank. So that is a ratio variable. So those are the main different types of variables. And so what I want you to take from this is that different variables have different properties, and that informs the type of analysis that you would choose. So this leads us to why this matters. This matters because statistical computations and analyses assume that the variables have specific levels of measurement. Different stats require the variables that are included in the stats to have specific levels of measurement. I'll give you an example here. Let's say we are calculating an average. It makes no sense to compute an average for a binary or nominal variable because there's no intrinsic ordering in the levels of the categories. They're just random. They're just arbitrary. It makes no sense to talk about an average hair color, but you can actually report the frequency. So you can report percentages and ranges in percentages, but you can't score an average from these variables. Average of an ordinal variable is often done, but it should be interpreted with caution. And again, this is because the spaces between the intervals of your ordinal variable are uneven. So in many cases, it's assumed, like there are certain circumstances where ordinal variables are assumed to have roughly even spaces, between the different ranks, but we can't always assume that. So you can calculate an average with ordinal variables, but you have to be very cautious with its interpretation. And an average is perfectly fine for interval and ratio variables because we assume that the intervals are equally spaced. Again, when thinking about a particular statistical analysis, there are some research design factors that you have to keep in mind. The main one, I think in my opinion, the more I think about it, it's probably the overarching main reason, the most important one is your research question. I think that it always comes back to the research question. What is the most appropriate analysis that will best address questions of your project? I've been in many scenarios and I've had many conversations where researchers have a specific analysis that they like to do, and they're really excited about this new analysis because it's hip and it's cool and we're all nerds and we like to flex our statistical muscles. And so they will try and sometimes mold and twist and distort the research question to fit that analysis. And that is wrong. Research questions should always guide the methods and the choice of statistical tests. Distinction is, are you interested in associations or predictions? So are you interested in how variables are related to each other? That is a very important consideration as well, because when you're interested in relationships between variables, that points to specific classes of analyses. And also, are the data that you're dealing with, are they unpaired or paired? I'll be talking about this in a few slides here, but are you looking to compare groups and conditions, or do you have data that repeatedly assesses individuals on a specific variable? So kind of like a baseline, follow-up time 1, follow-up time 2. Those would be more repeated types of designs, and those call for certain types of analyses. So that is an important distinction between the unpaired and paired, also known as kind of like independent observations or paired observations. So keep some of this stuff in mind when you're your own stats and your own projects or projects that you're thinking of doing, and how some of the stuff that I'm talking about may apply to your situation. All right, well, I hope everybody can still hear me. So what I've done here is I've come up with what I've called the Research Analyst Starter Pack. So this is what I've thought about this a lot, and there's a lot of different analyses that I thought I would pick from and show you for this presentation, but I've settled on the following 6. There's so many different analyses to choose from, but I've chosen these 6 because I think they will meet most of your needs. So my readings of the medical literature and the psychological literature and the sociological literature, and based on all the research proposals that I've had the opportunity to review, and also based on probably several hundred consultations with researchers and projects that I've been involved with, spanning many topics and content areas, I feel that these analyses will pretty much serve you well for about 80% of the time. So for the most part, these analyses will cover most of your projects. And so we will review some of them, and I'll give you pointers about what the purpose of these analyses are and what types of variables is included in these analyses. So I'll also point out real quickly that many of these analyses have different variations. So when we talk about ANOVAs, for example, there's many different types of ANOVAs. There's many different types of regressions, and a lot of these analyses have different options that can be customized. So I'm just going to stick to probably the most common forms of these analyses. But if you're interested in something more sophisticated, then feel free to reach out to me and any of the other very, very intelligent, very capable methodologists within research services. So the first analysis that I'll be talking about are the chi-square group of analyses. Chi-square, the main purpose of chi-square is to look at differences between two categorical variables. So you are comparing frequencies within these different categories, and chi-square comes in many different forms, but its most simple form, its most basic form, is known as the 2x2 cross tabulation, or the 2x2 chi-square. This includes two binary variables. So if you just look at the diagram here, so at the top, we have vaccinated. So we're doing our study, and we have a sample of many, many people, and we code them whether they were vaccinated, yes or no. So for one binary variable. And we also like another variable. This example, I came up with it a while back, but it's very timely. So the other variable that we would collect on these individuals would be the presence of influenza. Let's say it's flu season, so whether they had influenza, yes or no. And then we arrange the variables in this form, and the chi-square analysis can tell us if there's a significant difference between these variables. So we collect our frequencies, so 7 people vaccinated and had influenza, 86 people were not vaccinated and had influenza. And likewise, 91 people were vaccinated and did not have influenza, and 10 people were not vaccinated and did not have influenza. So you can see that there appears to be some relationship between vaccination and influenza, if I'm going out on a limb here. So this is what chi-square analysis will do for you. And also keep in mind that the percentages can be reported straight up and down the columns. They can also be reported across the rows. For these examples, I just decided to report them within the columns. So chi-square analysis can also be extended to other forms. So a more complex form is a 2x3 chi-square analysis. And so this example has one binary variable, so one kind of yes-no type variable, and one nominal, and you can also use it with another nominal or ordinal variable, and they can get really complex. Like you can have 4x5 chi-square analysis. You can have, I believe one of my colleagues was in the department was working on a project that had like a 3x20 or something like that. So they can get really, really big. I always encourage people to try and break them down to smaller categories. But let's say, for example, here we had at the top treatment adherence, poor, moderate, or high. On the left-hand side, we can see whether they had a cardiac event, yes or no. So we can populate our frequencies. And so we can see here that when treatment adherence was high, down here at the bottom right-hand corner, when treatment adherence was high, the rate of cardiac event being no was 98%, and it goes less and less as treatment adherence is poor. So if we go up here, when treatment adherence is poor, the rate of cardiac event is 89%. So this is very, very useful to looking at differences between binary and other types of categorical variables. So when doing a chi-square analysis, you would not enter a continuous variable into this type of analysis, because it makes sense, as you can see. The next type of analysis are the family of t-tests. There's several different types of t-tests, but here I'm just going to go over two, which are known as the paired samples and the independent samples t-test. Within the paired samples t-test context, the purpose is to compare before and after measurements on the same group of people. So you have some variable that you are measuring at one point in time and again at another point in time within the same group of people. So, well, let's measure on the same group of people at time 1 and time 2. For these types of variables, for these types of analyses, your dependent variable should be continuous, and your independent variable should be categorical. In case point 1 and time point 2. So we see up here we have a group of individuals at time 1 and a group of individuals at time 2. You notice that both people in these graphics are the same. So let's say that we assess their level of anxiety, depression, and stress in January, when this world was a much predictable place, and we assess their levels of anxiety, depression, and stress in March, when the world is crumbling down. And in the meantime, let's say that we had some sort of mental health intervention of some kind. Let's say these are just really stressed out people, really stressed out with their work. You can determine the impact of the mental health intervention pre and post anxiety, depression, and stress scores. So you can see whether these scores decrease over time, increase over time, or stay the same. So that is what that is what a paired samples t-test will tell you. The independent samples t-test, that thing's slightly different. You have two conditions. In many cases, you have a control and an experimental condition, and each condition has different levels of your independent or your predictor variable. In this case, the dependent variable is continuous, and your independent variable is binary. It's usually some grouping variable. It's males, females, young, old, disease present, disease absent, received some intervention versus not, and then you compare them on some outcome. So let's say we have our friends here who are very anxious and depressed and chronically stressed, and some of them took part in a yoga program and others took part in no such program. And so we compare the rates of anxiety, depression, and stress as a function of participated in the program or not. And you can see here in this infographic, in this graphic here, that folks, our friends here, are different individuals, I should say. And I guess the idea would be that the yoga program would have some impact on anxiety, depression, and stress. So if we ramp this up a little bit, so we're kind of building here, right? Like these designs are getting more and more and more complex. So if we go one step up from the t-test, we have what's referred to as in analysis of variance, specifically the one-way analysis of variance, also known as ANOVA. You've probably seen ANOVA or this acronym a lot in papers, but this compares two or more levels of an outcome. So if we go back here, we only had two groups. This is the limit of the independent samples t-test. If you want to add a third group to this, you have to shift over to the analysis of variance. So this is the same variable being measured across all groups of people. Again, your dependent variable should be continuous, and your independent variable should be nominal or ordinal. It should be some sort of grouping variable. So let's say our outcome is to reduce blood pressure. So these are very, very stressed individuals, as we all are right now. So we could administer placebo in one group, a drug at 10 milligrams in another one, and a drug at 20 milligrams at another one. Let's say it's a blood pressure drug. Or we can give them no dietary recommendations versus one type of diet versus a second type of diet, or maybe no therapeutic intervention versus one group gets cognitive behavioral therapy and the other one gets the CBT plus exercise. And we look at what their blood pressure ratings are over some time. So this is what one-way analysis of variance does. You can do a one-way analysis of variance with only two groups as well. So with the t-test, we had two groups that we were comparing. You can also compare two groups with ANOVAs. That's perfectly fine. They are mathematically equivalent. I think the F ratio is this. I believe the t-test is the square root of the F ratio that ANOVA will give you. So they're mathematically equivalent, but ANOVA just lets you add more groups. So getting even more insane, we now have a two-way analysis of variance. Now, when I say one-way or two-way, all that is referring to is the independent variable, the groupings. So in the case of one-way analysis of variance, add in these three examples here with the placebo, with the drugs and the diet and the therapy, we had so if we just focus on the drug example, in the drug example, we only have one grouping variable. Our grouping variable is drug condition. It has three levels: placebo, drug at 10 milligrams, drug at 20 milligrams. One variable, three levels. In two-way analysis of variance, we introduce a second variable. So two variables here, two grouping variables. Each one of them can have two or more levels, so it can get very complex. So the purpose here would be to compare two or more levels of two variables on one outcome. You can start adding a third variable, you can add a fourth variable. All these variables can have different levels, and that's when you get into factorial analysis of variance. I'm not going over that. That's beyond this presentation. So this example, let's say we have gender, males and females. That is one grouping variables, and with two levels. So males and females, those are two levels of this variable. And then we have, let's say, surgery, standard method versus a new method. Second variable with two levels. And let's say our outcome is improved quality of life. These are people with a lot of pain, and they undergo this surgery, the standard method and the new method, and then we measuring quality of life over maybe a 1 month follow-up. So as you can see here, we have a group of males who got the standard surgery, a group of females that got the standard surgery, a group of males who got the new method, and a group of females that got the new method. So this test allows us to determine the effects of gender and the effects of surgery on our outcome, which is quality of life. However, what the two-way analysis of variance will do is that it will tell you what the effect of gender is, it will tell you what the effect of surgery, but it also includes one extra one. It tells you what the interaction of the two variables does. So maybe there's no differences between males and females on the surface, maybe there's no differences between the two surgical methods on the surface, but when you look at the interaction of the two, there could be a significant difference. So it could be, for example, that females undergoing the new method tend to have significantly higher index of quality of life relative to everybody else. So it allows you to look at at each of your cells here, each of your 4 cells, determine if the improvement in quality of life was specific to one of the cells. So that is the two-way analysis of variance, and as I mentioned, there's factorial analyses of variance, which start introducing more variables and more levels. I've seen 2 by 2 by 3 by 5 by 3 variance before. So interpreting that is just, I don't know, it takes a long time to wrap my head around that. Correlation is another very common analysis that's very, very, very popular and very easy to do. And so correlation is a analysis that quantifies the relationship between two variables. This analysis produces what's known as a correlation coefficient, and the coefficient tells you about the strength and the direction of the relationship. So for this, you want to use, you can use 2 continuous variables, which is known as a Pearson correlation. You can use 1 binary and 1 continuous variable, which is known as a point biserial correlation. You can also use a 2 binary variables, which is known as a phi coefficient, and it just goes on and on. For correlation, it's a very general analysis, which means that it can be applied to a variety of contexts and a wide variety of different types of variables and different types of variable combinations. So for most analyses, most statistical programs, when you are doing a correlation in the analysis, you just enter your variables and then it'll just spit out the appropriate analysis, the appropriate type of correlation. You don't have to specify Pearson or point biserial or phi or Rho or Spearman or any of those other ones. Correlation coefficient ranges from -1 to 1, and the sign of the coefficient tells you its direction, whether the relationship is positive or negative. And the value will tell you the strength of the relationship. So if you have a correlation that's 0.5, you know that is a positive correlation. As one variable increases in magnitude, the other variable also increases in magnitude. You know that because it's positive, and 5 tells you the magnitude of that relationship, which would be quite strong. And a negative correlation would be a situation where as one variable increases in magnitude, the other variable systematically decreases in magnitude in relation. So that is the difference between positive and negative correlations. Negative correlation, I remember when I was first learning about this, I would always associate negative with bad. And that was very, very common. I remember that was something that our stats prof would yell at us for, because he was a very angry man. But negative correlation does not mean bad. It just means as one increases, the other one decreases. And values around 0 reflect non-existent or weak relationships. That means there's no relationship between the variables, so as one increases, the other one's not really doing anything. And lastly, the last analyses, or the last 2 analyses that I want to talk about, are linear and logistic regression. These are often used. They're very, very common. The purpose is to predict an outcome, one or more predictor variables. That is what both the linear and the logistic regression will do. However, there's some slight differences between the two. Simple linear regression is when you have one predictor and one outcome and they are both continuous. So you have variable X and you're trying to predict variable Y. And both of these can be continuous. On the other hand, when you're doing logistic regression, the variable that you are trying to predict, your outcome variable, is binary. It's no. So for example, say you're trying to predict hospital discharge. So were they discharged on time? The linear regression would, the logistic regression would be, were they discharged on time? Yes versus no. Whereas linear regression would probably try and analyze time to discharge, so in number of days, because that is a more continuous type variable. So that is the main difference between the two. It's the outcome. With linear regression, the outcome is continuous. With logistic regression, the outcome is binary. So you're trying to predict a yes, no, present, absence type variable with logistic regression. In addition, logistic regression can typically handle any type of predictor variable, whereas with linear regression, you're using continuous variables on both ends. With logistic, on the prediction end, you can have continuous and categorical variables, and on the outcome end of things, only binary. To step it up a notch, you can also have multiple linear regression and multiple logistic regression. So this is an extension of the first example. So in this case, the multiple part of multiple linear and multiple logistic just means that you have more than one predictor that you're interested in. So 2 or more predictors, you can have 10 predictors, you can have 20, it doesn't matter. Rules still apply. Within the case of linear regression, your outcome is continuous and your predictors are continuous. Within the logistic regression context, your outcome is binary and your predictors can be categorical or continuous. There are many circumstances where categorical variables are used within a linear regression context. This is not exactly kosher, but it can be done. So I've seen people enter categorical and binary variables to linear regression all the time, and these are just very these are just rules to help you kind of in your mind separate the two, but in reality and in practice, there is a lot of blend variables and a lot of blend of predictor variables going on. And an extension of this, which I won't go here, but I'll just quickly tell you about, is the hierarchical logistic and linear regressions. This is where you take your variables and enter them in a specific order. So you may enter variable x1 first, and then you may enter variable x2 next, and then variable x3 after that. So you can, what is the incremental relationship between all these variables on your outcome? Okay, so that is all I have for you. So the goal of this presentation wasn't to turn anybody into methods gurus or statistical gurus. It was just to give you a little bit of information. Maybe you learn a couple things to help you better decide what analysis would be most appropriate for your data. If you are still a little confused, or if you want to know more information, or if you have a situation that requires something more complex, please reach out to us at Research Services, myself, and many of my colleagues who are also methodologists, both quantitative and qualitative, would be more than happy to help you. And that is all I have.
That's great. Thank you so much, Donaldo. I think that's a great overview, and hopefully we'll help, like you said, a few tools to get people started and more informed as they continue to develop their protocols. Does the group have any questions?